So, good morning. This is the 16th lecture on computer control, and it is devoted to linear prediction and minimum variance control. Today we are going to speak about prediction. That is to say, you want to do some forecast in the future. Why is this important for our proposals? Well, everybody would like to know what is going to happen in the future. In particular, everybody would like to know what are the numbers that will come out of Euromilhões. But I'm sorry to delude you, it's not possible to make a forecast on that. And we will understand why, or at least a useful forecast on that. Independently of these general aims, prediction is important in relation to control, because you can think of a controller that's something that inverts the system by making inverts your predictions in order to drive your system to the position where you want it. Suppose that you describe your system by a model that allow you to describe where is the state of the system to be in the next time sample. And you say, well, I want it to be in some position that you specify. So what you have to do is to select the manipulated variable such that this value is attained. So you have a number of predictions that depend on the manipulated variable, and you select the manipulated variable such that the prediction is the value that you want. So there is a tight relationship between prediction and control. Now, this is an extreme case, and actually this controller is not a very good one. In most cases, it will yield very strong values, very high values for the manipulated variable. But things tend to be more interesting when instead of predicting the position of the output of the state of the system, or of the state of the system in one point in the future, you consider a sequence of future values for the system. Okay? And that's the idea of predictive control that we will explore a little bit in future lectures. So for the moment, let's try to consider the prediction problem, and more exactly the linear prediction problem. So to be more specific, suppose that you have a sequence of numbers. We call this a time series. So these numbers correspond to some variable that you sample at even time instance. So every second, or every 15 minutes, or every day, or every week, or every month, you measure the variable. So you have the value of the variable at discrete time 0, at discrete time 1. I don't know why it's not here, just because I forgot it. At discrete time 2, and so on. Okay, in general, you are at time t. Look at this plot. You are at time t. You have observed a number of samples up to time t, and you want to estimate the variable at time t plus m. Okay? So before moving on, I would like to ask you, how can we approach this problem? So at this point, the microphone is yours. A volunteer to tell me, or to tell everybody of us, how can we solve this problem? You do a number of observations of a time series, and you want to, based on these observations, make an estimate of the value of this time series m steps ahead. What can we do with the tools that we know about? No volunteers? No ideas? Are you listening to me?
Yes.
And no ideas to solve this problem?
Maybe you can use the RMAX model like we used previously.
We can use what?
The RMAX, this estimated model.
The decimated, can you be more specific?
Like the RMAX model, the one we used in the lab.
Okay, so we can use a model, and it could be the RMAX model, and then?
If we know the U, like the input.
There is no input here, okay? So we can get rid of the input. Okay, so use ARMA model. So the X part is, we don't have it, at this moment at least, okay?
Okay.
So later we will consider predictions for systems in which, or for time series that are controlled, in which we have a control variable. So for the moment, the problem is even simpler. So we don't have the U. U is 0 or it's absent. So you're saying we use the ARMA model. So the model that relates the observed values of Y with some noise that makes it shake. And then?
Can we estimate Y of t plus 1 up to Y of t plus m?
And we estimate Y of t plus 1, okay, that part I understood from the model, okay?
Yeah,
so
then Y of t plus 2 until Y of t plus m.
How do you estimate Y of t plus 2?
Once we have Y of t plus 1, we can use the same model to estimate
Okay,
Y of t plus 2.
We iterate the model. Very good, João, very good, okay? That's the idea. Now, we have a number of problems here, but the central idea that João brought out is use a model. So here I don't see any model, so how can we get the model?
Maybe linear regression or maximum likelihood.
We do some, we use least squares or maximum likelihood. Actually, if it is an ARMA model, we need maximum likelihood. So we estimate the data we estimate the model from the available data, and then we iterate the model, okay? One after the other. And we could also have used a state model, okay? What is important is that we have a model, okay? Now, we have one problem, which is probably, if we consider the ARMA model, the ARMA model says that Y is a linear combination of small shocks. That's the white noise, no? Going up and going down and down again, and then up and then down and up and so on, okay? So it's a stochastic model. So we have to deal with that, okay? So we have to deal with the fact that this is not pure deterministic. And we have to deal with that. And the other thing that we need to deal with is we would like to have some notion of optimality. I mean, some predictions are better than others. In engineering, this is quite important. Formulating a problem as an optimization problem. Okay? Perhaps the first guy who did that was Gauss when he invented least squares to estimate parameters from data. Here, you see, I want to estimate data from other data. It's a little bit different, although it's not so different. So I would like to have a criterion on the quality of my estimate of y of t plus m. Okay. So, okay, so before moving on, just the picture of two guys who were among the first guys to think about this in quite different ways. One was a Russian, Kolmogorov, and the other was Norbert Wiener, okay, who invented the word cybernetics because he was worried about the connection between control concepts and system concepts and living bodies. Okay, he did a number of experiments together with a colleague physiologist in which he showed that in a cat, the muscle of the cat was controlled by a feedback system. Okay, so he started saying, well, we are machines, so that we can apply the principles of system theory to living bodies and so on. He did that in the 40s and 30s, 40s, so 70 or 80 years ago. And he was quite a character. I mean, if you look at his biography, it's quite interesting, and it's full of anecdotes. Okay, he was a very distracted researcher, and he was mainly a mathematician. I won't tell anything about him now, but if you look in the net, you will find plenty of stories of Norbert Wiener. And for those of you who like livros de quadradinhos, comics, okay, comic stories. There is a character invented by the Walt Disney team, not exactly by Walt Disney, but by the Walt Disney team, with done after Norbert Wiener. Okay, he's Professor, is Jairo Girlus, in Portuguese, Professor Pardal. Okay, Professor Pardal was coined after Norbert Wiener. Okay, but that's another story. And actually, Norbert Wiener was considering the problem of prediction based on stochastic ideas. And as I was telling, the solution implies that you have a model that you can somehow iterate, and by iterating the model, you get the predictions. And the criteria to compare different possible predictions and select the best way of doing it. Okay? So we are going to consider as a model white noise filtered by a linear system. That's the ARMA model, okay, that João was mentioning. And the criteria, we are going to consider a quadratic cost. Could be other things, for instance, a linear cost, but let's consider a quadratic cost. Okay? So about the model, let's say something about the model. So we have some white noise. White noise, remember, we had studied things about white noise in the past, and this is not, in discrete time, this is nothing more than a sequence of independent random variables, not necessarily Gaussian. Okay, you can have non-Gaussian white noise. What is important for whiteness is that the number that you get is independent at one instant, is independent for all the other numbers. Okay, so you get this aspect. Okay, it's very easy in MATLAB to generate discrete time random noise, white noise, which is just use the function rand n. In that case, it's Gaussian rand. It's a Gaussian random number generator. Okay, so you pass it by a filter, and remember this filter tells you that y is a linear combination of past values of y and past values of E up to ET. And you get something which is no longer, you see, this is not so much interesting. I mean, you see something that you don't see any pattern here, but when you filter it, you start seeing a pattern, an oscillatory pattern. Now, I'm going to discuss the prediction of signals generated in this way. What do you think? Is this too limitative or not? Think about, suppose that you want to forecast numbers, different kinds of numbers. Okay, you can think of the coronavirus, number of infections per every day, or the amount of electricity consumed at Technico every day or every 15 minutes, for instance, or the amount of water consumed per day in Lisbon. So every day you have a number and so on. So does this model is adequate in these situations or not? What do you think? Suppose that you have a robot and the robot is moving, okay? And the robot is moving and it has some velocity, but due to irregularities of the terrain, sometimes it moves a little bit faster, sometimes it moves a little bit slower. Okay, but it's moving along some direction in a definite, with a definite aim. Would this be an adequate model for that? What would be the time series? Think of the robot example. What would be the shape of the time series if you have a robot that moves away from you with a steady velocity? Think of the position as a function of time. What type of curve would you get?
A linear curve.
A linear curve, so a straight line that with some slope, okay? Which is nothing of this kind, okay? What happens is that if you compute the average of the position of the robot, it is increasing every time, okay? It is increasing every time. Instead here, you have a system with zero mean, which is the white noise. And you pass it by the filter. And the filter, remember, does a linear combination of past values of the output, and that's it to past values of E. So you are always adding values with zero mean. So the mean of the output is zero. The expected value of the output is zero. Okay? So this is not able to model something which is quite common as a robot moving along one direction. Okay? So what is the problem here? How could we suppose that the velocity of the robot is not exactly constant, but it has some random fluctuations? Can you find some relationship between the model of the robot and this type of model, the ARMA model? What would you do? So you have the sequence of numbers that represent the position of the robot. The robot is moving in it's a straight line with some slope because the velocity is more or less constant, but it's not exactly constant. So you have some random fluctuations and you want to model that. So what would you do? When I say what would you do, is to relate the model of the motion of the robot with the ARMA model. Is there a place where you can use the ARMA model? How? If you differentiate the position, then you get a velocity which is more or less constant. Okay, it's not exactly constant. So the velocity of the robot would have probably such a pattern. Okay, so how could you solve the problem of modeling the position of the robot? You could differentiate, or if you want to then to do something else and predict the position of the robot, you differentiate, then you predict this signal, and then you integrate the prediction. Exactly the same thing that you have been doing when building the model of the flexible bar in the lab. Okay, it has an integrator, so you differentiate it, you get a stationary signal, you adjust an Armax model, and then you add the integrator. Okay, so in time series, you look at the type of time series that you have, and you say, well, this is steadily growing, so you differentiate it. You find a stationary system that can be modeled by white noise passing through a linear system. So you solve the problem of prediction for this stochastic system that remains, and then you integrate your predictions. Okay. Suppose that you have electricity. Okay. Electricity in one day, it has a kind of periodic variation, not exactly periodic, but I mean, the electricity consumption at 6 o'clock in the afternoon, it's very near to the electricity consumption of the same hour in the next day, and quite different, for instance, of the electricity consumption at noon in the same day. So what do? You differentiate by something that comes from a delay, that approaches a delay of 24 hours. Okay? If you are taking a sample every hour, instead, what you do, you pick up your signal and you differentiate it by 24 samples. Okay? You multiply by z up to minus 24. And then you have to do the inverse operation with the predictions. Okay? This is the so-called Box and Jenkins approach. This is not part of the subjects that I'm going to ask you in the test and in the exam, but it's interesting to see, to mention to you that you can use these ideas to solve very complicated problems with what you know by using just them in a clever way. Okay, so you do some kind of differentiation, can be a one-step differentiation for signals that vary like a straight line. You repeat that if it is a parabola, or you differentiate over longer periods if you have some kind of periodicity. Then you end up with some ARMA model. You do the forecast for the ARMA model, and then you do the opposite operation with your predictions. Okay, this was invented. This technique of forecasting was invented maybe in the 70s, late 60s, early 70s. And these two guys, Box and Jenkins, wrote a book that became famous, and they were working in the field of econometry. Okay, so making predictions about things related with the economy and money. These ideas instead, well, the first one to think about them was Wiener. Wiener was considering things in continuous time, which is much harder problem, because in continuous time you don't have this notion of white noise. Actually, white noise does not exist in continuous time. Okay? And white noise is something that has a constant power, constant value over the frequency spectrum. This means that the power is infinity, and you don't have signals with infinite power. Okay, so you have to, the derivatives do not converge, so you have to redefine what you mean by a differential equation and so on. That's quite exciting subject, but we don't discuss them here. Actually, Wiener wrote a report with a yellow page, and he wrote that during the war. It was a secret report, and no one could understand it anyway. Only probably a few people could understand Wiener's report. And they were making a joke, telling that this was the era of peril, o perigo amarelo, making a double sense with the fact that the Japanese were the enemies. And it was just after the war that two people wrote a simplified version of Wiener's work. And later, in the 60s, so about 20 years later, a researcher called Carl Ostrom, he was working at IBM Research Center in Sweden. And IBM Research Center in Sweden was very much concerned with pulp production, produção de pasta de papel. And so he developed a computer controller, to produce paper with the same thickness. We are going to see what was this algorithm, this control algorithm. Okay, and he solved this prediction problem in discrete time, which is much simpler. And as we are going to see, this amounts just to do a division of polynomials. Okay. Now that I confused you with all this trash, let's go back to our problem. So I assume that my signal, y of t, I want to forecast it, and it satisfies this model. It's a linear system that filters a sequence of white noise, that is to say, of uncorrelated variables, et. So yt is c divided by a filtering e. Okay, and I call this the autoregressive moving average model, because autoregressive y depends on itself because of the a polynomial and on its past samples. And also it's a moving average, it's a linear combination of et and its past due to the c polynomial. Okay, let's look at the equations. So instead of using the forward shift operator, I'm going to use the backward shift operator. So suppose that you have a polynomial that I called a star of q minus 1. Q minus 1, remember, is an operator that backward shifts the signal. And a of q is 1 plus a1 q minus 1, a2 k minus 2 plus k, a3 k minus 3, and so on. Okay? And there is a notion which is a reciprocal polynomial. This a star of q minus 1 is the reciprocal of polynomial aq. aq is q up to n plus a1 q up to n minus 1, and so on. Okay? Actually, this is a definition of reciprocal polynomial. Now, suppose that you have your model aqit equals to cqet, and you multiply by q minus 1. So you delay everything by n samples. By definition, q minus na is a star, the reciprocal of q minus 1. And q minus nc, q, is c star of q minus 1, and q minus 1. So you started with your model written in the forward shift operator, and now you write it in the backward shift operator. Okay, This helps you understanding what we are going to do, this model. Okay, that's the model. Now we have the criterion. So I call y hat of t plus m given t, so this vertical bar, you should read it as given e, as the estimate of yt plus m given observations at time t. So you are at time t, you have done observations up to time t, and you want to estimate y of t plus m, and I call this estimate y hat of t plus m given t. Okay? Now, if I subtract it from y of t plus m, I get the error. But the error by itself has no meaning because this is a stochastic signal. So I take the expectation of y of t plus m minus y hat of t plus m given t squared. Okay, I square the error and I take the expectation. But this expectation is conditional. It's a conditional expectation. So it's given the observations up to time t. Okay. So my problem is how can I find y hat that minimizes this? And I'm assuming that y verifies the model, the ARMA model. That's a problem. Okay. Now, what are we going to do? You have your model, and I write it instead of at time t, I write it at time t plus m. Okay, so here instead of yt, I get yt plus m. Instead of et, I write it at et plus m. And instead of having c divided by a, just by the previous slide, you know that you can replace this by c star divided by a star. Okay, so this is a polynomial in backward shift operator divided by a polynomial in backward shift operator. You can expand these polynomials treating q minus 1 as a variable, okay, and using the division of polynomials, something that you have studied and probably forgotten in high school. Later, we are going to see how to do this in practice. What is important is that I expand C star divided by A star as an infinite series. I'm assuming that C star and A star have no common root, so this is an infinite series. Okay? And I split this series in two parts. Okay? You see? Two parts. And one part, you see, ends here. You start 1 or q0, q minus 1, etc., up to q minus m minus 1 or q minus m plus 1. Okay? Minus m between brackets m minus 1. Okay? And here you have q minus 1, etc. Now, if you think of C star divided by A star applied to Et plus M, and you apply these operators, what you get? 1 filtering Et plus M gives you E of T plus M. F1 Q minus 1 E of T plus M gives you F1. Et plus M minus 1 because it delays 1 unit, etc. And this last term gives you Et plus 1 because you have E of T plus M delayed M minus 1. So this is T plus 1. Okay? And the other terms, the other parcel gives you things that start on Et minus 1, Et minus 2 up to Et minus infinity. Okay? So I have split my y of t plus m in two parts, as a sum of two parts. One is made of future noise values, and the other part is made of noise values up to time t. remember that you are in time t. Time t is the importance of time t is that it's a time in which you do the forecast. You have observed things up to time t. Okay. Now you can write this. We don't like infinite series. So I write here a polynomial. Okay, this is finite, this term here. I call it Fm. So Fm of q minus 1 is nothing more than 1 plus f1 q minus 1, etc. Fm minus 1 is this polynomial. And this is an infinite series, but it's nothing more than some remainder divided by aq. Okay, so Fm is the quotient up to m minus 1, and q minus m gm is the remainder, o resto of the polynomial division. Okay, so we can write actually this in a very compact way, in this way. Okay, we are going to use this in a moment, but look at this formula. Look at this formula. We don't observe E, so this is not practical for making a forecast about Y, because you don't observe E. But probably you can relate E with Y using the inverse model. Okay? Here you have terms that correspond to values of E that have already materialized themselves. They have manifest. They have done their job. They exist at time t. These are the future terms. Okay, and they are independent from this one. So if you make the expected value of the product of this first term times this first term, you get 0, because all the terms here are independent from all the terms here. Okay, so the expected value of that product is 0, because the expected value of their product is since they are independent, it's the expected value of the first term times the expected value of the second, and they have both of them have 0 mean. Okay, so they are independent. This part here on the right depends on noise up to time t. So things that have already existed, probably you can obtain them by inverting your model at the top. And things here are things that they will depend on the future with respect to time t. So what is your guess about the prediction here and probably the prediction error? Do you have any guess? Do you have any feeling? Alguém tem eu decompus o meu sinal na soma de duas parcelas que são independentes uma da outra. Uma tem todas as coisas, tem todos os ruídos até ao instante t. Eu não consigo observar os ruídos, mas eu consigo, se calhar, escrever isto de uma maneira independente, de uma maneira equivalente, que envolve os y, invertendo o modelo. O C e o A têm tantas raízes um como o outro. Portanto, C e A, C sobre A é causal e A sobre C também é causal. Portanto, eu consigo recuperar o Y a partir do E e exprimir tudo em Y. Okay? Isto é tudo o que aconteceu até o instante T. E aqui eu tenho o que acontece de T mais 1 para a frente. Alguém tem um palpite sobre qual é a relação que estas coisas têm com o preditor e com o erro de predição? Apenas um palpite. Depois vamos ter que provar as coisas. Ninguém tem nenhum palpite? No? Okay, so let's move on. Actually, what I'm going to show you is that this term is going to be the predictor, and this term is going to be the prediction error. Okay? So the term on the right, made of things that depend on noise up to time t, is your prediction, optimal prediction in the sense of minimizing the least squares prediction error. Or the squared prediction error. And this other term is the prediction error. Okay, let's do it. So this equation is something that will be your companion in solving these problems. Okay, so you divide two polynomials, c divided by a, as the quotient. I call it fm star, q minus 1. And then we have the remainder, but I know that the remainder is at least of order q minus m. So I put a q minus m here and I write g star m. So q minus m divided by or multiplied by g star m is the remainder that is divided by a. Okay, so this is nothing more than the formula for the quotient of two polynomials. Okay. Now, look at your model. Okay. So replace c divided by a by these two terms. Okay, by these two terms. So your y of t plus m is fm. There is a et plus m missing here. Sorry, et plus m missing here. Plus the other term, q minus m applied to e of t plus m gives you e of t. Okay, so this is e of t, and there is a e of t plus m here. Okay, so the first term is a linear combination. The first term is a linear combination of e's between t plus 1 and t plus m. Let's look again at the previous slide. It's this linear combination. I call it fm applied to e of t plus m. So it's a linear combination of et plus 1, et plus 2, up to et of t plus m. And the other part is made of, and it's an infinite series actually, that corresponds to et, et minus 1, etc. So it's the present and the past. So this term is the future, and this term is the present and the past. And both terms are independent. So the expectation of the product of these two terms are 0, because since they are independent, the expectation of the product is the product of the expectations, and each one has an expectation of 0. Okay, so I call it epsilon m as fm q minus 1 e of t plus m. So that, don't forget that there is e of t plus 1 missing here. Okay, so we have the model, and now we plug the model in our cost. So where I had y of t plus m, I place this term plus epsilon of t plus m. Okay, this term here plus epsilon of t plus 1. So I just rearrange things. Now I group this part here with my predictor. My predictor is a kind of deterministic quantity on the data. So I group this together, and then I have that epsilon m term. And they are both independent because epsilon m depends on et plus 1, et plus 2, et plus m. And this term here depends on et and its mass. So I have expressed all the quantities here apart from the y hat, which is a deterministic quantity that I want to select. I've expressed them as a linear combination of white noise, and this linear combination is independent from this linear combination. So that's why the expectation of the square of A times B is 0. Okay, so when I take the square, of everything here, what happens? I take the square of the first, okay, the square of the first. I take the square of the second, plus the cross term, which is not here because it's 0. Okay, and now I've repeated this here. I have the expected value of the square given observation up to time t. But this is something that happened up to time t. So I can compute it exactly because I know everything up to time t. I know all the observations, and I can compute the corresponding e's based on the model. Okay, using what? Using the model. Using the model. Where is the model? This model. Okay. So what is? Let me ask you one thing. What is the expected value of x, random variable, given that x equal to 5? For sure it's 5. Okay. So the expected value of this quantity given things or variables that allow you to compute this quantity is exactly this quantity. So you can get rid of this expected value. Okay? Actually, this is a mathematical theorem. A mathematician would last about 3 hours to explain you this. But intuitively, we are computing the expected value of a quantity given data that allow to compute the quantity. So it's just this. Okay. Now, here we have the expected value of epsilon squared given data that are independent of epsilon squared, epsilon m squared. Okay. And this is the same as having the expected value of epsilon squared. Okay. Because this data is independent from what is here. Okay. Again, intuitively, we can accept this. A mathematician would give several lectures to come to this point. Okay, Professor Jean Xavier gives a very nice course on stochastic networks, and he takes several lectures, and it's quite difficult results to prove this to equalities, but intuitively we can accept this. Okay, now our J, remember the J, look at the J. The J is the expected, is the expectation of the squared error conditional on observations up to time t. And we want to estimate to find out y hat that minimizes this J. And we could write it as a deterministic quadratic form, a deterministic function, sorry, of y hat, plus something that does not depend on y hat. Okay? So this is a scalar. What is the value of this quantity that minimizes this square? Clearly is when the basis of the square is 0, or when y hat is gm divided by a star filtering et. Okay, so the optimal predictor is this. The problem is that you don't observe E. So what you do, you use the inverse model to generate E from Y. Okay, so you use the inverse model, and from the inverse model, assuming that all the A's have roots inside the unit circle, when you remember we have discussed that when you do the cut, this A with that A, we are forgetting about terms that correspond to transient states that go to zero. In steady state, your predictor is this one. Okay, so this is a linear combination of past values of the prediction, because you have this C star, and GM applied to YT is a linear combination of past values of your data. Actually, the fact that you assume that A has all the roots inside unit circle prevents non-stationary data. Remember that in the beginning, if you have non-stationary data, you have to differentiate it along different periods to get rid of these poles that are over the unit circle, for instance. Okay, so what is the conclusion? What is the conclusion? The conclusion is that suppose that you know C star and A star that generate your YT. So what you do to get the C star and A star, you apply maximum likelihoods to your data, and you get C star and A star. That's another business. Okay. Suppose that you know say C star and A star. Okay. The optimal M steps ahead predictor is given by this filter. Is given by this filter here. That filters your data. And GM is, I call it the remainder, but actually Q minus 1 GM is the remainder. So when I say GM is the remainder, is with a slight abuse of language. So I do this polynomial division. If I want to do predictions 3 steps ahead, then this FM is of degree 3 minus 1, that is to say 2. Okay, and so I get FM, which I'm not using here, but I will be using in a moment. And the predictor depends on GM. Okay, so this is the optimal filter. So from C and A, I do this polynomial division, get F and G. So you know that it's F star M, but I just say F because I'm a lazy guy. And G, when I say G, I mean G star M. Okay, so by long division of the polynomial C and A, I get F and G. And G immediately gives you your predictor. Now, one thing that you have to quantify is the noise. So remember that your quadratic error is this term here, and you selected your prediction to make this vanish. But then you have something which is the expected value of the square of epsilon m. Okay? And remember that epsilon m is a linear combination of future values of E. And these terms are all independent. So if you expand everything, all the cross terms, say E of t plus m and D of t plus 1, E of t plus 2 and E of t plus 3, and so on, all of them will not contribute, will be 0 because they are independent. The only terms that contribute are the expected value of y squared of t plus m, f1 squared, expected values of e of t plus m minus 1 squared, and so on, of the squareds at the same time. And the expected values of the square of the several samples of V are just 1. So you get 1 plus F1 squared plus F2 squared and so on. If you have some power of E, which is not 1, you have to multiply it by sigma E squared. So this is the power, that's the expected value of E squared. Okay, so this is the power. Okay, this is the variance of your prediction. The standard deviation is the square root of this. And you know that your prediction will be plus or minus 3 standard deviations. Okay, with 0.995% of probability. So your predictor is given by the output of this filter, GM divided by C, and your variance of the prediction is given by this formula, where these F's come from the F polynomial. It's the quotient polynomial. At this moment, you are lost, but let's see some examples. Suppose that we have these two polynomials, and I want to compute predictors 1 step ahead, 2 steps ahead, 3 steps ahead. Okay, so my C star divided by A star is given by this. So I put here my C star, and I put here my A star. And then I start finding out the coefficient here, such that this coefficient multiplied by the leading term here vanishes the leading term there. So this is 1, this is 1. So I should have a 1 here, because 1 times 1, when subtracted from 1, gives you 0. Okay, so I put a 1, I multiply everything, so I put polynomial, and then I subtract. This is 0, and then I subtract the terms. Now, I'm going to select the next term such that this second term multiplied by 1 again cancels the first term here. So this is very easy, because this is 1, this is minus 0.2 q minus 1, so this is minus 0.2 q minus 1. So I multiply everything here, minus 0.2 q minus 1, plus 0.24 q minus 2, and so on. Okay, so this polynomial is this polynomial times this polynomial, and then I subtract. The leading term vanishes, and so on, you see? So I progress this way. Now, here I get the F polynomial, and here I get the remainders. This is remainder for 1 step ahead predictor, the remainder for 2 steps ahead predictor, and the remainder for 3 steps ahead predictor. I think I have something like this. Okay, so F1 is 1, F2 is 1 minus 0.2 q minus 1, and F3 is 1 minus 0.2 q minus 1 minus 0.14 q minus 2. Okay, and don't forget these remainders are multiplied by q minus 1, q minus 2, q minus 3, but only the remaining part, G, is always of the same order. G is always of the order 1. Okay, in this case, because you are dividing by a polynomial of the order 1. Okay, so your G1 is minus 0.2 plus 0.1 q minus 1. G star 2 is minus 0.14 plus 0.08 q minus 1, and so on. Okay, the 1 step ahead predictor. So I pick up this G, I put them here, and it's G divided by C. Okay, filters Y of t. This means what? This means what? If you expand this, and you multiply both sides by this polynomial, you get y hat of t plus 1 is equal of 1.4 y hat of t plus minus 0.5 because it's on the other side, on the right side, y hat of t minus 1 of t minus 1. And then minus 0.2 yt and 0.1 yt minus 1. Okay, so I'm using nothing more than this formula here. Okay, gm divided by c filtering yt. What about the prediction error? I look at the first term for the one step ahead prediction error. It's just 1. So it's 1. If the variance of the noise is 1, it's just 1 squared. 1. Now, for the 2 steps ahead prediction, for the 2 steps ahead predictor, I look at this polynomial. So G2 is minus 0.14 plus 0.08 Q minus 1. And the F polynomial is made of these 2 first terms here. Okay, so I write here my G2, and here I have the squares of the coefficients of my F polynomial. Okay, and the same thing for the 3 steps ahead predictor. Questions? No questions? You are all smashed. Estão todos cilindrados.
I'm sorry.
Yes?
I have a question.
Okay. If you feel uncomfortable speaking in English, you can speak in Portuguese and then I will translate. Go ahead. Who?
I have a question.
Alex? Okay.
Yeah. Hello. I
You
was
don't
trying.
speak Portuguese. That's why you were puzzled. Okay, good.
Yeah, exactly. It's about the project. I was trying to find the deadline for the next project. Do you know when it is?
You should speak with Professor João Pedro Gomes.
Okay.
Okay.
Thank you.
But about what I just said. Any question? Alguma pergunta sobre o que eu acabei de dizer? Okay, so let me make a short review of what we have learned today. We want to solve this problem. We have a sequence of numbers, no control, just a sequence of numbers. And you are at time t, you have made a number of observations up to time t, and you want to estimate the value of the sequence of numbers m steps ahead. Okay? And you assume that your numbers are generated by white noise that passes by a linear filter. So you know this linear filter. And your criterion of estimation is minimize the least squares error given the observations up to time t. Okay? So what was the technique? The technique was to pick up your model, write it to write y of t plus m that you don't know, that's the quantity that you want to estimate, and split y of t plus m in 2 parts. In 2 parts. One contains all the data and the other contains things that you don't know. Okay? And both these parts are orthogonal. So taking advantage of these 2 quantities and the fact that they are orthogonal, I plug my model in the cost and hocus pocus, I get this formula for the predictor. Okay, and how do I split y of t plus m in two parts due to this division algorithm, to this polynomial division algorithm? Okay, so this was the technique that we followed. Any last question or any last comment? No? Okay, so we will continue tomorrow. We stop here. There is, if you look at the slides, there are some slides now for the situation in which we have a dependence on the control. Okay? I won't speak about you now for concerning this. I will speak to you later. We move to the control problem, and then we will go back and look at this problem of prediction in the presence of an external variable u. Okay, but if you want to, when you read the slides, you can read the slides up to the end of the prediction section that comprises the effect of u. Okay, so we will meet each other tomorrow.